So for this, we're starting to look at working with scatter plots and looking at the ideas of correlation in particular. And we'll spend a few lessons introducing correlation and correlation coefficients. But essentially a scatter plot is something like this, and we've seen them before. And we're comparing data between two different sets. In this example here, we're comparing how far someone can jump horizontally to how high they can jump vertically. That's it. There's a lot of kind of data mentioned here. Let me just get straight to the first worked example. I have a scatter plot here. In this case, I'm not saying what the x and y axes represent. Just keep in mind, in general, whatever's on the x-axis, that's our independent variable. It's usually the x. We use x, but this is our independent variable. And whatever we put on the y, we treat as the dependent variable. Hopefully that sounds familiar. That's it. I have a scatter plot here. And the point in red is the mean point, which just means the x-coordinate is the mean of all the x parts for the data, and the y-coordinate is the mean of all the y parts of the data. And so the first thing I want to do is create a line of best fit on here. And it would help if I have a ruler, and let me grab one. There we go, got a ruler. And so a line of best fit is a line, or a linear function, that best approximates the pattern or the trend, we say, of the data we have here. And for now, I just want to talk about sketching a line of best fit just by looking at it and using a ruler. And a general sort of strategy that tends to work well, if you want to visualize a line of best fit, is find your mean point, which I've already shown there in red and highlighted, and draw a line that goes through that point, and then not only roughly matches all the points we see, but try to have roughly as many points above the line as below. And so if I do that, I get something roughly like this. And that's my line of best fit. And again, it goes to the point, it kind of shows us visually the trend that we're seeing. And this trend matches the line quite well. So we call this a linear correlation, that the points here seem to form quite closely the pattern of a linear function. Now, there's many types of linear correlations. When we have points that go downwards, or a line of best fit that has a negative slope or a negative gradient, we say it has a negative correlation. If the slope was going up or had a positive slope, we'd say it has a positive correlation. As well, though, we can talk about how closely the points relate to the line we see here. And in this case, these points do really quite strongly connect to the points. What we see here is an example of a pretty strong correlation, but a strong correlation in which it's going down. So what we see here, the scatter plot, we would say has a strong negative correlation. An example of a weak negative correlation would be if the points were still going down generally, but not as closely clustered to this line of best fit. And a positive correlation would be similar to this, but the points would be going upwards. So again, what you see here is an example of a very strong correlation, and it's a negative correlation because it's going down. Now here I have another scatter plot. This time I tell you what the data represents. And this is showing you the scores for 10 students, and so each point represents a student, and their scores on 2 different tests, each out of 30 from a grade 9 math class. So the x-axis represents their scores on one particular test, and the y-axis was the score on another test. And each of these points here represents some student. So for example, the student here looks like they got roughly 17 out of 30 on the first test, and it looks like they got 11.5 out of 30 on the second test. And again, we have a line of best fit shown in red. Now, the line of best fit in this case was actually made using technology. It's called a regression equation, and we'll talk more about that later. But first of all, as I can tell from looking at this, there's definitely a positive linear coefficient. These points generally cluster close to this. Not as close as, it's not as strong as a correlation as we saw in the previous question, but it's definitely a positive correlation. But I want to measure this correlation. And so Pearson's correlation coefficient, or just Pearson's R, is a measurement of how closely these points resemble the line. And in general, if I go back here, we have the correlation coefficient, or R. It's always between -1 and 1. If the correlation coefficient is exactly 1, which we almost never see, that means all the points are exactly on the line, and there's a positive slope. We call that a perfect positive linear correlation. And that's if every single point is exactly on the line of best fit perfectly. In general, for data, we don't see that, but that's one extreme. The other extreme is when R is -1, in which all the points are still perfectly on the line, but the slope is negative, and it's going down. We call that a negative linear correlation. And again, those are the extremes. We rarely ever see that. In the middle is a correlation coefficient of 0, in which there is absolutely no best fit line that can be shown. There is absolutely no correlation, we say, at all. And again, we usually don't see that. Usually we see something in between 0 and 1 or 0 and -1. And so for this particular one here, the correlation coefficient, the R is definitely positive. So R is definitely positive. Sorry, R is greater than 0, I should say. It's impossible for R to be greater than 1. It's definitely not 1. If it was 1, all these points would be perfectly on the line. Maybe not evenly clustered, but all on the same line, which it's not. If it was just barely above 0, it would be almost impossible to even see how the line of best fit connects to the points, which I can see there's a connection here. So in general, this is a pretty strong correlation between the points and the line of best fit, which is not surprising. It's not surprising to know that in general, students, how they perform on one test tends to relate to how they perform on another. But it's not a perfect correlation. You don't have to do the exact same on one or the other. And so for this, if I was to estimate, it's definitely a positive number. It's getting closer towards 1, but it's not that close to 1. And so we would estimate this probably around 0.7. And if we look back here, please keep in mind a 0.7 correlation, we say, is kind of the border between a strong and a moderate correlation. And so what you're seeing here is really right on the border between a strong correlation and a moderate correlation. There's definitely a relation between the scatter plot we see in the line, but it's not as strong as the previous example, like right here. All right, so that's my estimate. Now let's actually figure out what it is using technology. And so for this, you need to be familiar with your GDC, but these are the actual scores for the 2 tests for these 10 students. And so these are all the scores for one test, and these are the scores for the second test for the same students. So for example, I can see this student here scored 20 out of 30 on the first test and 16.5 out of 30 on the second test. Now, depending on what GDC you're using, the exact process of how you find this differs. But in general, as with anything else we've done in statistics, we want to create a table using these values. This would be our X, this would be our Y, or this would be our first column, this would be our second column. And then if you're using the TI-84, which is what most people are using, you want to find linear regression, which is one of the menu choices when you go to the calculator option. But when you do that, you should, and again, this is where you just got to be familiar with your own, you should see several different statistics about or measurements about this data, but the one we care about is the R, and the R value, which is being calculated by the GDC, comes to about 0.728. And so that is accurate to 3 decimal places, and you can see my estimate was quite close. And so again, I'll just write this down formally now that we actually have this. Again, this is an example of a moderate to strong positive correlation. And so in terms of interpreting the significance, that just means that, yeah, there's a pretty strong connection between how a student performs on one test compared to the other. It's not surprising, and now we have a bit of data basically to back it up that, yeah, these two are related. But again, it's strong to moderate. It's not a very, very strong correlation, which means depending on what these tests we're assessing, there's the differences between them. Keep in mind, I will just add that when you found your Pearson's correlation coefficient, Pearson's R, you probably also saw details of the line of best fit. For example, the line of best fit you get, if you may have seen this on your device, is 0.74x plus 6.16. That is the line of best fit that actually you see graphed in red right there. And we don't need that right now, But that is the equation of the line of best fit using regression, using what the calculator did, and we'll talk about more of that in a later lesson. So for the last question, I want to look at this data, and I want to fill in the blanks so that we have a nearly, but not quite perfect negative linear correlation, which means I want an R value here that's really close to -1, but not quite -1. So how can we do this? Well, first, if the correlation coefficient is going to be negative, this has to represent something that has a negative slope, which means if my first point is at 0, 100, all of these have to go down. So what I want to do first is I want to make a perfect negative linear correlation, which means I just need a linear pattern. So whatever happens from here to here, let's say it goes down by 10, so that's now 90. I'm going to keep doing that. 80, 70, 60, 50, 40, 30. So if I were to take the time to put this into my GDC and calculate Pearson's R, I know I would get R of exactly -1 because I know these points make a perfect linear function and the slope is going down. So this is a perfect negative linear correlation. I want something nearly that, but not quite, which means all I got to do is change one of these numbers. I can do more than that, but I'm just going to take this 70 right here, just because, and instead of 70, I want to change it to something close to 70. And I'm going to change it to 65. So now I know this is no longer a perfectly linear correlation, but it should be very, very close. And if you actually now put all this data into your GDC and you calculate Pearson's R, you will get -0.997. Extremely close to being a perfect negative correlation, but definitely not perfect. And I'm done.